Hello again. Tonight, it's going to be postulation time again. To understand how the universe might have begun, first postulate how it might end. Yeah, it's kind of a clickbaity title, but it's such a long title that I had to end it to understand how the universe might ... And that some places that's as much of the title as I could fit. But we'll get into the details of it. So yeah, it's me postulating once again, but here's the scientific method. If you come up with a question, a poser, there's nothing stopping you from doing your research and saying, I think, but then somebody's got to go out and test it, come back with empirical evidence to prove that it is or isn't what it is that you said, analyze the data, and then if there's a conclusion and it's valid, thumbs up. If it's not, thumbs down. Keep the cycle going. Next. Well, in the case of the universe, we have a problem. And the problem is nobody was around at the beginning. Nobody that's ever been born on this planet was around when the universe came into existence. So we have to, even as science, postulate, go get data, make observations, look back as far as we can in optical and then infrared and now microwave. And there's a barrier that we get to, which is just a microwave haze, cosmic microwave background. And it's hard to see further back in time than that. But maybe someday by doing gravity waves better, we might look in gravity waves. And we already like positing that there might be a cosmic gravity wave background. So the way that we're doing this now is we do things with particle colliders. And the particle colliders show if you have these circumstances under this environment, then you can make things happen. And we're extrapolating that if that's the thing that happens at the subatomic level, then that is one means by which you could have a Big Bang. And so that's what we're basing it on. But that's not definitive proof. That's just the evidence that we have available to us and making a prediction. But until we go off and build our own universes, we have no way of proving it. So the actual start date, I looked it up on NASA's site, and NASA's saying that it's approximately 13.77 billion years ago, with a tolerance for some inaccuracy. And that's understandable. But we also have space telescopes out there that, based upon gravitational lensing, we can evaluate the Doppler shift of light that we're receiving. And we evaluate it as, wait a minute, that thing that we just saw is older than that 13.77, 14.4. Now, this is an individual star within a cluster of galaxies. So it's a very small number of pixels of light that we're picking up. And we're judging from that the actual wavelength and saying, it must be that old. But at 14.4, it's close enough to 13.77 that that's in that fudge range. But they now have one even older that's like twice that old. It's called Earendel, and the Hubble Space Telescope discovered it through gravitational lensing. And now they're saying, well, 28 billion is kind of not within the fudge factor of 13.7. That's a lot older. So there is a scientific study in the work queue for the James Webb Space Telescope to go look at Earendel and see, well, let's look at a second instrument evaluating the second star, this same star within this same distant cluster of galaxies, and see if it comes away with the same analysis, because it's got much newer instruments and such. The difference being the Hubble Space Telescope can see in towards the edge of deep infrared or far infrared, whereas the James Webb Space Telescope can't see down that far into infrared. It can only see mid-infrared. So, you're comparing apples to oranges here. Something that might have been able to do it had they found it and then tasked it and it was still around, would be SOFIA, the 747 infrared observatory, but it's not there anymore. So can't get a second opinion from SOFIA. And apparently it didn't observe it back in its day. So how do we observe even farther back? Well, you go from optical to infrared to deeper and deeper infrared to microwave radio. Well, you can't use an optical telescope for microwave radar or microwave radio. You have to use a giant antenna. We have one of these already. The difference is, if you remember the KH-11 spy satellite that was pointed down at the Earth, and then, hey, that's a good idea. Let's make a Hubble Space Telescope, take the basic design and flip it outward. Oh, prescription's wrong. Yeah, okay. Well, this would be the same thing. We want to take the commercial company that created Blue Walker 3, and we want to flip it to point out in space because it has a synthetic aperture radio telescope that can pick up microwaves down on the Earth. Well, if we put this out at Lagrange point 2 and we face it so the antenna's out into space, we can actually go in wavelengths below the cosmic microwave background and see what we can see. But until we put it out there, we won't know what we can see. So the changes would be, let's see, it's about the same size, 10 meters, 33 feet. Yeah, we can build a phased array like that. Solar panels, big solar panels. Yeah, we can do that. The panels have to point back towards the Earth because at L2, that means also back towards the sun to get its power. The antenna has to point obviously out into space on the dark side of the solar array to keep it cool. Obviously, we need an additional communications antenna pointed back towards Earth so we can talk to it and get data from it. But that would be deep space radio astronomy's equivalent of a Blue Walker 3. We have the technology. We just have to have the right people that, control the purse strings to open it up, let some moths come out and spend a few $1 million. So there are predictions for what happens at the end. Not quite exactly when, but what happens at the end. But it's a safe bet to say that anybody that's on this planet or in the future on this planet for some time to come won't be around when the universe actually ends, if it's going to end that many billions of years from now. Because think of it this way, the sun's going to end in about 4 billion years. Long about the same time frame, Andromeda and Milky Way are going to swirl within one another. So our galaxy won't exist. Our sun won't exist. So if there's people, we should have moved off to another exoplanet by then. But there are bigger things in the universe that are drawing us towards them. Not our solar system, not even our galaxy, but all the galaxies that are in the cluster of which we're a part. And there's several of them. There's one called the Great Attractor, which they actually used as a joke in the Men in Black first movie. And then there's, not to be confused with the Great Wall of China, there are these large areas that kind of seem like they're some kind of outer shell of the universe, and stuff's moving towards that. So there's different velocity vectors that collectively say, well, we're not moving that way, and we're not moving that way. We're kind of moving somewhere in between because we're being drawn by both of them. Whichever one will win out, we don't know. But also the actual expansion of the universe. Well, you can see the plot lines here. Well, depending upon what your evaluation is of dark matter and dark energy, whatever they happen to be, pick a number and it'll give you a curve. And the curves all go out like, an unlimited number of billions of years. Where will it all end? We don't know. But of course, we could figure out where it'll all end if we just solve one little problem: temporal technology. If we either create something that can go there, gather the data, and then come back to where, from which it was sent, we could have evidence, hard, fast, empirical evidence. Or if we could kind of like open a hole, go grab, bring back, close the hole. And I'm not talking like wormholes. which these zigzaggy things that you see in sci-fi movies, I'm talking about more like a grommet, where you open the hole, it's immediately on the other side, do what you need to do, bring it back, close the hole. So 2 forms of figuring this stuff out without having to wait until the end of the universe and without having to guess and guess and guess based upon, flimsy evidence what happened back then. So some of you might recognize the first 2. Doctor Who's TARDIS and the old Time Tunnel series. The one at the bottom is, okay, the Max streaming service had a show on that lasted 4 years. It was part of the Warner Brothers DC universe. It was called Doom Patrol. And in the last season of Doom Patrol, one of the characters that was from an earlier time found that they could create a time machine. And the doofus part of it is, see those screwy things that look like corkscrews? This time machine would actually invert itself and drill through the planet and like a worm and then pop up at a different time. More than science fiction, just goofy. But that was the essence of Doom Patrol, is goofy. So if you have one of these 3 things, you could go to the end of time. Now, once the Earth was gone, I don't know how the Doom Patrol time ship would work. But, I'm not going to hold it out for the rest of the universe to say, nobody that ever existed or will ever exist will ever figure out temporal technology. I'm not going to hold the rest of the universe accountable to our ignorance. The Vulcans never believed in time travel, and they were proven wrong. So we know about the endpoints of stars. And I've got this lovely picture from the NASA Night Sky Network, and you can see top center, sun-like star. That's where we are now. And then it goes around to the left, and you get a red giant, and then a planetary nebula, and then a white dwarf, and then what? Well, that's the end of the postulation, is white dwarf, and then it will cool down for many billions of years, ... What happens after that? They don't have an answer for that yet. I have an answer for that. It's called a black dwarf. And a black dwarf is essentially the remnant matter of a white dwarf after it's cooled well down below the fusion level. And now you have left a thing floating around called a black dwarf. And I'll be studying the radio emissions of one in the latter part of December. Evidence for postulation. But this is a star, and we have the same thing for massive stars, big blue supergiants that become super red giants and supernovas, and they'll either form a neutron star or collapse down into a black hole. And those are those endpoints. What happens after it's a neutron star? Well, for billions of years, stuff will happen. Does it become a quark star? Is there a midpoint between the two? Verdict's out on that. What about the black hole? Oh, Hawking radiation. That's just where somehow the energy will bleed off of it over umpteen billions of years, and the black hole will just dissolve away. Pull my other leg. So it's a mixed bag, but we actually have evidence for when things become, neutron stars and white dwarfs and such. In spectral analysis of the gas clouds that are around them, we find that there's still some sign of helium and often signs of hydrogen even after the star goes boom. So even after the star goes boom, there's some helium and hydrogen left. And if you have enough of it, that can coalesce back into nebulas and next generation stars. Now you might think, what's the evidence for that? Our solar system. Our star is not a first generation star. It's at least a third generation star. Well, how do you get a third generation star if that first new supernova took out all the possible hydrogen and helium and you have nothing left to fuse? That's because it doesn't. It takes out a lot of it, It consumes a lot of it, but there's still some left. So maybe it makes less huge stars. And do that again and again, and you'll get a cascade of generations of stars. But apparently there was enough hydrogen and helium after our progenitor stars of our solar system in the giant nebula we were once a part of that we could form the sun, Jupiter, Saturn, Uranus, Neptune. Lots of gas left over to fuse. Plus all the slightly heavier stuff to make terrestrial planets. So whatever amount of time you think it would take for everything to just like run out of steam, run out of fusible hydrogen and helium and whatever, it's actually a lot longer than that because some remains. So then in 1967, Andrei Sakharov came up with this concept of proton decay, that protons just kind of over a long enough period of time through interaction with all sorts of bosons, literally just proton falls apart, decays, and you get a meson containing a quark and an antiquark, and maybe some positrons, which are antimatter electrons. And it all sort of interacts and just gone. Just energy. It sounds good. It looks good, as the saying goes, on paper. But even in particle colliders, we have no direct evidence of protons actually doing this. We have lots of evidence of things that are smaller, subatomic particles that are, antimatter particle elements and quarks and things like that. We know those don't last a long time and they dissolve from antimatter interactions and just become energy. But today we don't have any evidence of that for protons, even though Andre has this lovely postulation of this is how protons go away. Now, this is not the same thing as when you get radioactive decay and an atom ejects a proton and changes from one element to another. That's transmutation. And it's not the radioactive decay when a proton under intense forces gets transmuted into a neutron, as in neutron stars. This is literally the proton falling apart. But that's their way of saying eventually all matter will end because all matter has protons and therefore all protons will end and the universe will just gone. A long time from now. Long, and even longer than you think from now. Because there are two regenerative forces that the people that are postulating the end of the universe don't think about, even though I know they know it. So hydrogen and helium, we know that fusion consumes those, converts it into energy, higher order elements, and okay. But there is also radioactive alpha decay of heavier elements like uranium, thorium, some others, that produces extremely stable, fully ionized new atoms of helium-4 and even trace amounts of helium-3 through tritium beta decay. So we have buried within the Earth these heavy radioactive elements that are producing helium-3 and helium-4. And we know this because we detected helium on the sun in spectral analysis as, what's that? Before we detected it in places on Earth as spectroscopic analysis of volcano emissions. And we went, hey, there's something coming out of the Earth. Looks a lot like that stuff up in the sun. So yeah, we actually discovered helium on the sun before we discovered it coming out of volcanoes on Earth. But we also found out that liquefied natural gas wells also spew out helium. From deep within the Earth, we have decay occurring, making helium. So the Earth annually produces about 3,000 metric tons of helium. And each day we lose to space about a ton or so of helium. But space is enormous, so the percentage of helium compared to the universe is very small, so the total doesn't noticeably increase, except when you start saying, oh, every terrestrial planet that has radioactive material at the core is all spewing a little helium. Now, there's how many hundreds of billions of stars in our solar system, in our galaxy, and how many of those have planets that may be terrestrial and therefore spewing helium. Now, you get enough of this helium together, influenced by gravity, you have gas giant planets, they condense down new stars. So just because a star consumes helium does not mean there is no more helium. Same thing is true for hydrogen, although it's a different process. Radioactive decay splits water molecules in deep ocean water and in water that's chemically bonded into subsurface rock that's near these radioactive decays. And therefore, you have the water being split into hydrogen and oxygen as peroxides and radicals, which generally will chemically bond with whatever's nearby. But a small amount of that hydrogen doesn't have enough to bond with and therefore bubbles out of seawater and never to be seen again because it disappears up in the sky. Now, the amount being generated is small, but the total volume of it being generated by the Earth is larger. Earth annually produces tons of hydrogen and loses tons of hydrogen due to bonding and out to space. But even though the percentage is small, the total throughout our solar system and throughout the universe is going to be high. Again, gravity collects this, produces future generations of stars. So even though fusion is removing hydrogen, radioactive decay occurs long after the stars no longer exist and long before they existed, so more. So it comes down to subtraction and addition. Are we, as a universe, consuming hydrogen and helium faster than the collective processes of all the planets on all the solar systems in all the galaxies are producing hydrogen and helium? Nobody's doing the analysis, so most people would just ignore it and go, no, not possible. Have you measured it? No. Then how can you say it's not possible? So there's some that's being consumed, there's some that's being produced. I think non-existence is going to take far longer. There's many more intermediate generations of stars that will be produced well before we ever run out and consider proton decay. So the universe existed long before us silly humans did and will long exist after us silly humans are gone. We don't have to worry about the beginning and the end because probably somebody in the future with a far greater awareness and appreciation of their existence and their potential, likely with far more developed science and technology, access to more abundant resources, less constrained by dogmas, groupthink, or delusions of grandeur like we've got it all figured out. They'll figure this out. But right now we can postulate. But we humans may postulate all we want, but we've got some problems. So what is our opportunity for advancing the universe's awareness of itself? Somewhat nil for some time to come. Expansion of human society around the universe. The universe is very big. Even our galaxy is very big. So our threat to the universe is nil for some time to come. What about our threat to our own existence? That's considerable. We do all kinds of bad things, and we're more of a threat to ourselves. So we need to get a clue, clean up our act, and start behaving ourselves. War is not the answer. But many of the people on this planet still think that light speed is impenetrable. Some think that the universe is only about 14 billion years old. Some think that they're the only intelligent life in the galaxy, let alone the universe. And even some of them still believe their planet is flat. And my favorite owl picture.
You should take one like that.
I have lots of, I would never, ever say that I'm anywhere near his caliber. Wouldn't even fake it. So lots of links to various things, multiple pages of them. And then if you need background, what is a pion? What is a positron? Comments, questions, critiques,
No, it's pretty good.
more things in heaven and earth
So
than above in your
for
philosophy plate.
for some of the galaxies, the older galaxies that we see, the galaxies that look like a yellow disk, or the ones that look like a cigar, those elliptical galaxies, they are about to consume most of the gas. So the rate of manufacturing new stars, it's slowing down because their lack of stellar nurseries. Our galaxy right now is very young and still has lots of stellar nursery. So normally stellar nursery is about 20 to 50 times the size of the sun, like in mass, the mass of the sun. And then as the galaxy ages, it starts to depleting all the gas. The only way for the galaxies to get new gas, to have the new generation of stars, is to collide with other galaxies. Then the gas collides and you have a new generation of formation of stars.
The amount of time that heavier elements are going to exist between the formation of stars is longer than the existence of stars. And if the radioactive materials, when they decay, are producing hydrogen, are producing helium, they're going to be generating longer than the stars took to consume it. Now, will it balance out? I don't think so. But will it run out as fast as being predicted? I don't think so.
Monroe?
Yes?
Sorry, could you say that again, but a little bit slower?
Okay. So when a star goes supernova, it produces heavier elements. Some of the heavier elements it produces are radioactive, and they decay. Within the Earth, there are radioactive elements that as they decay, they release helium. They release helium in two forms, helium-3 and helium-4, to the tune of hundreds of tons per year. But it's trapped underground, or it escapes through volcanoes or oil wells, and therefore we lose tons of helium per day. Very small in comparison to the rest of the universe, but it is a regenerative source of helium. Now, if you multiply that up by all of the fissionable material that makes up all of the terrestrial debris in a galaxy or in the universe, collectively, it's not a trivial amount. It may be not sufficient to completely replace, but it's enough to have a next generation of stars form without, being impacted by other galaxies that have lots of hydrogen and helium. And turns out hydrogen undergoes a similar process, that the radioactive decay splits water molecules either in deep oceans or trapped in the water elementally within rocks. And therefore you generate lots of hydrogen. And same thing holds true, but you're generating less hydrogen than you are helium, because a lot of the hydrogen that gets generated immediately chemically recombines with the nearby materials, but there's a percentage of it that does escape. And when it escapes, it just bubbles up through the ocean and goes off into space, and you never see it again. Individually, on a planet basis, that's not much. But if you say, how many terrestrial planets are there in our galaxy? Billions. How much collective hydrogen are they releasing back into the galaxy? A number greater than zero, but we've never evaluated it, so we don't know. We can't say an insignificant amount, and we can't say a significant amount, but it's a non-trivial amount.
Yeah,
which
I think it is a trivial amount, because you compare the mass of terrestrial planets in this solar system. The mass of the terrestrial planets is trivial compared with the mass of the sun. And it's like, if you're only observing the terrestrial planet's hydrogen, it is vestigial. Now, if you could add the larger planets and the sun, but the whole thing is that the production of stars, it starts to slow down when all the material is being converted to heavier materials and stuck in stars for a long time until those protons decay. And you have to think about that the prediction of the cold universe is around after the degenerated era, where you start with the last generation of stars forming and dying. So, like the galaxy will stop to produce those stars, and then you have to wait for the degenerative era will happen only when the last red dwarfs, cool forever. And then from this point, you have to think that there will be a point where the dilation of the universe is going to become so big and so big that starts to weaken the galaxies in the centers. Then they start to spilling out all the material, and the universe becomes like slowly spilling out all the leftover material until they decay. And this is like 100 trillions when the degenerated era starts. That's when the last red dwarfs will die. And the materials giving back to the galaxy, it's not like big enough to make the new generation of stars. They can give the heavier materials for the new generations to a point, but when you have too many heavy materials, those have materials in the cloud. If the cloud has not enough mass, it will not collapse back, forming stars.
There is no evidence that protons decay. There's no physical evidence of it.
No.
Not even particle colliders have proven it.
It is.
So the dissolution of protons at the end of the universe is a postulation.
Calculated.
Just is. Another thing is, when a star explodes into a supernova, it forms radioactive elements. The radioactive elements will exist for billions of years longer than the star itself did. And if the radioactive element decay produces hydrogen, helium, it will be doing so for many billions of years longer than the star existed.
Yeah, but the remnant of the star is heavy enough and has most of that mass.
But it's uranium. Uranium decays, thorium decays, radium decays. When they decay, they produce hydrogen.
Not the whole thing, part of it. Like uranium decays, but the end of decay is lead.
Right.
Only a tiny little fraction decay to hydrogen. Oh, to helium. And helium doesn't collapse into stars. It's part of what is left over from the Big Bang, but what makes stars ignite is the hydrogen. Without hydrogen, there is no ignition.
Hydrogen is produced through radioactive decay as it interacts with water molecules, and it splits them through electrolysis. So hydrogen is being produced as a byproduct of radioactive decay in the presence of water. And the water can be chemically bound into rock and it'll still occur. Mm-hmm. There's lots of studies of this. Deep ocean, radioactive decay, splitting water molecules, producing hydroxyls.
Okay. So you have a decay, and normally they produce energy, and then they can break apart an existent molecule of water.
Yes, the water is deep ocean water or water trapped in rock.
Mm-hmm.
Yeah.
And so, that happens,
Yes. So radioactive decay produces hydrogen as well as helium.
Radioactive decay produces helium that during the process of decay, they could split water if they are in presence of water.
They are in presence of water. They've actually detected the hydrogen being produced in deep ocean vents. So
sure. Okay.
Subsurface material, the uranium's decaying, it's producing hydrogen as well as helium, and it's coming out, bubbling out through a vent, and they measure the presence of hydrogen. So,
Okay.
yeah.
That makes more sense. I thought you meant
How is the hydrogen being produced? I get the helium
It's-
because that's just alpha
so
particles, right?
during the decay, there is enough energy that can cause the water tube being broken apart.
Yeah. It's just electrolysis.
It's not a decay. It's not a decay. It's like you're zapping the water with some kind of energy and you're breaking the water apart.
The uranium has to decay before it can do so, though. So the uranium is producing an alpha particle, and the alpha particle is splitting the water molecules.
Or the photons or the heat resulting out of it.
Could be the heat, yeah.
Well, obviously, in principle, that's possible because you can stick a couple of wires on the ends of batteries and put it in some
Sure,
water and
yeah.
split it
Yes.
up. So,
Yes.
so
now just do that on a very
yeah.
large scale. Let's say planet size of high density pockets of uranium and thorium. You have heat, you have alpha particles, you have subsurface water, you have water trapped in rocks. You're producing helium and hydrogen.
Well, I would sure rather agree with Monroe because Helen is so gloomy with the heat death of the universe. But it seems to me that
It's the
1% of
most
1% of 1% isn't
Yeah,
much
it's-
math.
it's the
hope-
most
hope-
established hypothesis is the cold universe.
I just think that if proton decay does exist, and if we are to run out of hydrogen to make umpteenth future generation of stars, that it's going to happen umpteenth future generations farther out than we currently think it will, because when a star goes boom, there is leftover helium and hydrogen, and that's how you get multi-generational stars. How many times does that have to occur before you just can't do it anymore? We don't know. And if there is new hydrogen and new helium being produced in the cores of planets that's going out into space, a single planet's not going to produce enough to create a new star. But a galaxy worth of them might.
Yeah, but then they're so spread out.
Yeah.
Right? And then you need enough gravity to bring them together, and the proportion of hydrogen and helium to the heavy one. I'm afraid
Helium
Helen,
will
we should
not-
all kill ourselves right now.
Yeah. Helium will not fuse, it will not cloud collapse into stars. It's necessary to be hydrogen for the star to ignite, and that it needs to be enough for it, like the regular clouds that we see around us in this galaxy, they're around 20 to 50 solar masses. That's what we observe what is happening now.
To produce what kind of star?
Many kinds of stars, depending
No. What's the smallest one?
Red dwarfs.
What's a brown dwarf?
Oh, yeah, brown dwarfs. But I mean the ones that are fusing.
Okay.
Yeah, brown dwarf.
What's the smallest red dwarf?
Brown. No. You're correct. Brown dwarfs would be the smallest ones.
Yeah. So we don't know what that number is at the moment.
Probably most of the mass of the galaxy is brown dwarfs and red dwarfs.
Exactly. Where'd they get all the gas from?
They already got.
Where did they get it to form?
They already got from those stellar clouds.
Where? Okay. And where did the interstellar clouds get it from?
From the beginning of the Big Bang, and they
After multiple generations,
conglomerate and form galaxies, and
after
on
multiple
the gravitational
generations,
waves, they come together to form the generation of stars on those gravitational waves on the galaxies.
it would have to be multiple generations because
Sure.
they don't last that long, and the universe is multiple times older than that. So, yeah.
You already can see a lot of older galaxies. They're elliptical, that the rate of stellar formation has slowed down.
Hmm.
There is no areas of when you find clouds. They're just like a blurry, and they have like a kind of cloudy around that you can see it's made of the leftover hydrogen, but that hydrogen is just spread out in the elliptical or cigar-shaped orbits. And so now all the largest stars had died out, and they have only the yellowish color stars, the ones that live longer. And there will be a point and those galaxies will start to look redder and redder because the yellow stars are dying, and then they will leftover stars will be, the red stars, and until the galaxy loses the brightness. But most of the gas is already locked in the corpses of those stars that formed and die.
As they accelerate away, they become red as well. So how do you distinguish them losing hydrogen and only forming smaller red stars versus their
Not
accelerating?
forming, it's what is left over. The stellar formations end. That's what, and then that phase will last for maybe 100 trillions of years.
Was our galaxy ever a quasar?
Yes, most
What
likely.
was the level of stellar formation when it was a quasar?
I don't know the level of formation of,
It was
but
different.
maybe lots.
Yes, we find out that the
And
level of
probably
stellar
the
formation
galaxies
is
slow
different.
down.
Yeah.
And then when we collided with other galaxies and we stole the gas of the other galaxies, we started new phases of galaxy formation. We probably came back to be a quasar until, so let's say in the case of our galaxy, when we collide to Andromeda, we're going to have another stellar burst until it gets old enough that there's no more galaxies to collide in this area here. And then, it will become an elliptical galaxy, and then we will be redding until you get red galaxies, and that phase is gonna last trillions of years.
When Andromeda and Milky Way collides, isn't it supposed to form spherical before it forms elliptical?
Well, it's going to be misshapen for a long time, but during the phase of collision, the gas will collide, and those gases will form the new generation of stars, or Milkdromeda.
Mm-hmm.
Remember, the stars are so far apart that they almost never collide. What collides is the gas.
Like asteroids in an asteroid belt.
Yes, exactly.
Yeah.
They rarely collide.
Yep. But they do interact with one another.
Yes.
Which explains why the sun bounces up and down in the disk of our galaxy. Okay. Wow. A lot of discussion, and we're still ending early.
Yes. And I'm already dying because I'm in the habit to sleep early and wake up early.
Okay, I'm going to stop recording.